Okay, we are live. Hello, world. I'm Milen, your host, and we're waiting for my colleague Peyo to finish the session before. And meanwhile, I want to remind you to ask your questions in the chats window from the right-hand side, and also to engage with the virtual booths. It seems that you are so engaged with the presentation that you don't visit our booths. We took so much effort to preparing those booths, so please just take a look after the presentation. There will be a 1 hour break before the discussion panel. So hello Peo, you're just on time. I leave you. Good luck, guys.
Thank you very much, Milan. Well, hi Holly, hi Fernando. Let me
Hey, Bea.
start with a simple introduction. We are an extremely lucky position to be able to partner with perhaps the biggest consultancies in the world to deliver a very interesting project. But you have a special place, enterprise knowledge have a very special place in my heart, and you have actually earned it. Because you guys at EK, you never cease to amaze me how capable, how thorough, and how diligent you are. And actually, this is a great pleasure because we have been introduced to your leadership. And the more I know the people who are working with you, the more I'm really fascinated by your capabilities and your expertise. So today you have a very topic which is quite interesting to me. And without further ado, please share as much as you can for the time allotted.
Thank you for that introduction. It's lovely to be here. Hello to everyone. We are Holly Maykow, Fernando Aguilar, and we are representing Enterprise Knowledge for our presentation here today on identity graphs entitled Customer 360 and its Applications, a Case Study. So, a bit about Enterprise Knowledge. We are, after that wonderful introduction by Peo there, we are the largest dedicated knowledge management consultancy in the world. We are over 70 expert consultants based in DC with a global presence as well. As for who our clients are, we have a combination of federal and commercial clients, and we're helping them solve their knowledge and information management problems. Our consultants are experts in everything from knowledge management strategy and design, technical and software solutions, content strategy, and our personal favorite, knowledge graphs with data modeling and artificial intelligence and machine learning applications. So a bit about me. So again, I'm Holly Maykow. I'm a senior data specialist here at Enterprise Knowledge. And I am, as for my background, I am an engineer with a background in data and information management. I've been in this field for approximately 10 years. With EK, my focus is that data and semantic engineering pipeline, everything from requirements analysis, data mapping, ETL, to populating those knowledge graphs that we know and love. And a bit about Fernando.
Thank you, Holly. Thank you, Peo. Hey, everyone. I'm Fernando Aguilar. I'm a senior data scientist at EK at the Data and Information Management practice. I specialize in graph-powered machine learning solutions. And I'm really excited to be sharing this kind of knowledge share with you today because I've been involved in this project for about 2 years now, and I've been involved in ideation, and we're about to ship to production, so it's very exciting.
Excellent. Let's get started here. So what are we talking about today? So our theme is identity graphs. So first we'll tell you a bit about what an identity graph actually is, sourcing the data in order to build one, processing it to actually populate it, the technology and architecture involved, assessing whether your graph is actually doing a good job. And we'd be remiss if we didn't talk about potential roadblocks and considerations to take into account when you're embarking on a knowledge graph endeavor. So first, that technical definition, an identity graph or ID graph, it's a collection rather of known entity identifiers that can be associated with one another. These associations provide that comprehensive, stable, and ever-evolving view of a particular entity. So basically, you have your entity that you're trying to know essentially everything about, that 360-degree view. And in order to actually build one, you're first going to need to establish a use case, decide what information is actually going to be relevant to achieve your ends of getting that 360-degree view. Then you're going to be mapping out those specific characteristics and how they relate to one another, which, as you know, it's a graph. We have to have those relationships. Identify sources that are going to get you the information that you actually need to populate your graph. And then the most complicated and time-consuming part of this is determining how to reconcile all that source information that you have and to distill it down to the best version of each entity you're talking about in your graph. So why would we want to use an identity graph? Well, as I said, we're talking about that 360-degree view of the entity. So it's all-inclusive, cohesive, everything you want to know that you've designed into your graph. I will say the definition of an entity can depend depending on what you're talking about. We can have customers, products, employees, all here, you see below with that 360-degree view. For an example of that the customer side of things, this is a basic, very basic identity graph about features for a financial services customer, specifically with respect to their bank account and the mortgage on their residence. So you can see there at the middle, it centers around an individual ID. We have characteristics like their residential address, connected to their mortgage lender, their bank, their online banking profile, their phone number, and all these relationships that show how they relate. The purpose for this would be for the client to not only understand who are their clients, who are your customers, who are your employees, who are your anybody, what's everything about your entity so that you know more about them and can better serve them. But also you can use this for business decisions. If you were this financial services client and you had all this information about your customers, you'd be able to make marketing decisions, branding decisions to understand who are you actually trying to target based on the information you have about your clients. And without further ado, a little bit about our case study that Fernando has been involved in for so long, and I've been involved with too. We were presented with a massive challenge. Our client is a multinational firm that's collecting consumer data from hundreds of primary sources. So not, just two sources, hundreds of sources, with the goal of building a consumer marketing database. The data had varying degrees of quality, varying degrees of information from each source, and our mission was to distill it down to this customer 360 situation and get the best version of their target population that we could with the information available. So what did we do? We combined an ontology with data pipelines that involved matching algorithms in order to take all of this data, synthesize it, and distill it down to the best version of their clients or their best target population for what their goals were. So results, basically, ontology plus machine learning equals this persistent identity, so evolving as the data evolves, customer 360 view, identity graph with automated reporting and a vast reduction in the amount of time it takes to actually build. So they were happy. Talking about that data, I said for this particular project, we had hundreds of sources. I mean, your project can have varying numbers of sources, but the types will be the same. You'll have physical data sources and digital data sources. For physical data, this is things like postal data, census data, government data that is readily available and accessible about the physical aspects of your daily life, your name, your address, where you live, that kind of thing. We also have your digital data sources. In the case of our financial services customer, we could talk about credit agency reporting, mortgage reporting, things from your credit checks, bank rewards, all of this that you could compile together to get the actual data for that graph I had showed a couple of slides ago. And now that we've talked a whole lot about the data that you can use in order to build an identity graph, Fernando is going to take it from here and talk about the actual process of using it.
Thanks, Holly. So you can imagine there are multiple steps involved in creating an identity graph solution. However, these three steps I consider to be the three major ones. So data preparation. Once you have all your sources of data and you're ingesting the data, it is a good time right now to explore it, get to know it, and standardize any fields that you can. So if you're getting, for example, addresses, phone numbers, emails that follow certain field requirements, it's good to start standardizing them and validating it at this stage. You can also start filtering information that you really don't need to make it to the end individual, so that you end up taking a load of your graph. Next step would be your identity resolution. This is where all the information you have gets distilled into the actual entity. So you have multiple information coming from multiple sources. You apply these matching algorithms, and they get assigned to a particular entity. And once you have all this information about your entity, you start applying those features. So let's say you're interested in your consumers to see you're pushing a new pet insurance product. You want to know if they own pets. However, after these matching algorithms, you can have several sources indicating that your customer actually has a pet, and some sources that might even say that individual doesn't. So in this step, you actually establish rules so that you can say if your entity has a pet or not. And this could be anything from getting the most frequent value all the way to creating very complex models that can get you that result. Now, in regards to matching algorithms, we have two categories: deterministic, which is basically a human developed rule that you say, if you have information with these particular features, they belong to the same individual. This could be anything from account number, mortgage contract number, bank rewards number, or anything that could be associated to a particular individual. And you can deterministically say they belong to the same person, or in a broader sense, to the same entity. On the other hand, you have probabilistic matching algorithms, which could be approximate string matching, which they provide stochastic process to say a record belongs to an entity. This approximate string matching is most commonly known as fuzzy matching. And that's where knowing your data comes in very handy, because you can see if you're sourcing data from America, it will look very different than sourcing data from France in regards to typos, misspellings, alphabet used. So you can expect certain typos to happen with, let's say, US American keyboard configuration, and certain other kind of issues with a French keyboard configuration, right? So this comes very handy. You have fuzzy algorithms that can go through misspellings, typos, and even pronunciation. And you can also have infer data linkage, which means, let's say you have information about IP addresses or gathered relevant to a particular IP address that is used by multiple people. You can have algorithms that can infer who that record belongs to by using by modeling the behavior of that interaction, by applying other indicators such as resolution of the screen they're using, the type of operating system, etc. So we do these two matching deterministic and probabilistic matching algorithms. You have the full spectrum to distill that information into actual individuals or entities. Now, it's all great. Like, how do you come up with those algorithms? Well, first, like I said, knowing your data is going to be of greater importance in here, so that you can start thinking of algorithms. Am I trying to deal with typos? Am I trying to deal with misspellings? Am I trying to deal with inferred data? So you start narrowing down the algorithms that you're using. Then you're applying algorithms to the data one by one, so that you can start seeing the results. And then you have to determine how accurate those algorithms return, right? Compared to a ground truth. I'm putting ground truth here in quotes because with identity graphs, this will be the greatest challenge to arrive to. Let's say you're having an employee 360 identity graph, and ground truth would actually be getting all of your employees to self-validate the information that comes back at them and saying, hey, is this information really you? That would be like hard ground truth, which is unfeasible. And for most use cases, this would defeat the purpose of having an identity graph at all. So there are other means by sampling and really by defining your business rules in regards to how comfortable you are with a ground truth that it's not based on actual reality, right? So, and we can have a couple of examples here. So how would your algorithms deal with two people with the same name who are your employees but in different departments? And you have information regarding Jane Smith, that just happens to have a homonym in a different department, and you have information regarding this James Smith. How would your algorithm handle that? Who this information gets assigned to, right? And it could be assigned to either of them. Would you be able to tell the difference? Would you be able to say this algorithm was wrong? And another example would be if you're tracking your consumers and Jane Smith suddenly gets married or decides to change her name and changes her name. And you have two different individuals, like in real life, in different points of time. How would your algorithm handle that? How would it associate these two different names to the same people and infer that they changed names? Or would it create two different individuals? Those are some challenges that come from algorithms and that require that you know your data and that you document very thoroughly what you expect to get out of these matching algorithms, and that you have a basic threshold of how comfortable you are with some information will actually be wrong. Now we've been focusing on identity. Let's shift our focus now on graph. Why graph? So identity solutions are not new. They've been around for decades now, but they've been commonly being used in relational databases. So you can think having multiple information about multiple entities with multiple features attached to them and getting linked by a rigid schema. It's not very optimized for what an identity graph is meant to do, right? So graph provides a better structure given that you have highly interrelated data. Not all features apply to all individuals, so you can have sparse data, and you have a flexible schema that allows you to add new sources, change your ontology, which is the perception you have of the entity, and even add new features as you see fit for your use case. Now, what do all identity graphs need to have to function, right? Well, a no-brainer is it should be able to take data. It should be able to do identity resolution matching algorithms in real time so that you always have that most current view of your entity. It should integrate with your systems, and at some point it should also have a compliance feature built in if you're dealing with personal information, depending on your jurisdiction and your use case. Now, not all ID graph solutions are created equal. So like I said, matching algorithms are actually created based on the source of the data and the use case that you have at hand. So all of these matching algorithms are proprietary. All of these ID graph solutions will use their own matching algorithms. They would also differ on the data sources that they're using, depending on the industry they're serving and the use case that the identity graph was created to solve. Now you will be thinking, should I build one or should I buy one? If you want full control of your identity resolution process, you are better off building one, because since already built solutions tend to cater to a broad client base, they will have these proprietary matching algorithms of which you will have little to no access to, and they might be difficult to change or to make them more fit to your use case. Right? This comes in handy when you need custom rules that accommodate a unique case or compliance issue that you face. And if you're building this identity graph as a standalone product of service, then you are building your own identity graph. When does it come handy to buy? Well, if you are really not interested so much on all the information out there, but just that is particularly referring to your consumers, then you can have access to readily available data that can enhance your user information. You can opt in to buy a made solution, right? And if you have no access to third-party data, or if it's out of scope on your project or your budget, then buying a solution makes more sense.
On the topic of building and buying, we would be remiss, as I said earlier, if we didn't discuss potential roadblocks and things that you should consider when you're embarking on this identity graph endeavor. Whether you're building or you're buying, all of these things are important to consider as you're considering your use case and what you're going to do with your identity graph solution. So we have here a set of metrics that you can use to describe or to determine whether your identity graph solution is actually performing the way that you want it to, and as best as it can. We need something to be able to measure it by. So first, Match rate. This is the percent of overlap between all the known identities and those from the identity graph. So say you were talking about your employees, you know who all of your employees you have the list of employees, and you want to determine how well is my graph actually determining this from using all of the information that I'm inputting. Is it actually producing matches? This brings up to the second part of that, which is addressability. This is still the percent overlap, but it's only the percent overlap using deterministic matching. So as Fernando was talking about, matching on those employee IDs, customer IDs, some kind of identifier that's going to be known. If this is true, then it is a match. So it's taking out the stochastic and probabilistic matching and just using those deterministic algorithms in order to get that percentage. So when you take your match rate and then your addressability, you put them together and you can see how well your graph is actually doing in terms of actually getting you good matching. Third, super important for everyone, especially if you're using this for constantly updating your plans, speed. You want to know how long is it going to take to process all of the data that I have input to get me results. Who is my target population right now? Who are my customers right now? You want to be able to make those decisions and not have a super long lead time before you can actually make a decision, especially if you want to stay current depending on your market and your use case. Fourth is usage information. What applications are actually using this knowledge graph? You get these results. Then the question is, what do you do with them? How many different processes are actually using this information? Are there other downstream applications and end users for those? How many of them are there? You want to know what exactly your graph solution is actually fueling. And this is important not just for reporting and for you to know where your information is coming from, but to know when you actually make a change all the way up with the graph and any algorithms or data that's coming in, you want to know what those downstream effects are going to be, and you can predict where you're going to see changes in your results and what that will mean, especially if you're tracking things over time on a short-term basis. You don't want to see a massive pivot in those results and not have a reason why. Lastly, we were talking about for the project that we are so proud of over here, that idea of a persistent identity, being able to evolve what it means to be that customer, that employee, that product over time as different data is input, new data is input and incorporated into the graph. So we need to know how often are you importing new information into the graph. So when can you expect to get new results? What is the level of your persistent identity? So if you combine that with the usage information, you can see when you're getting these updates, when you can expect those updates, get all those downstream effects. So when you put all these things together, you can tell that we have a full view of how well our graph is actually matching, and then see the effects of the downstream applications and what all of that information is ultimately fueling. Lastly, considerations. Again, we have to talk about it. Back at the beginning of the presentation, I said you have to have a very defined use case for your identity graph. What I'm talking about there is those business specifications. What is it you want to know? What are you going to use it for? And detailing out all of those steps. What data am I going to need? What questions do I want to be able to answer? You need to separate your business and technical specifications. You wouldn't try to program something without knowing exactly what it's for. That's not productive. You would also end up with a technical solution that doesn't quite meet what you're talking about, which ultimately isn't going to fuel the ends for your actual use case. So decentralize business and technical specifications, business first, technical second, and then make it iterative if you see that the results aren't exactly what you need or something isn't working as effectively as you think it should. Second, we want to plan for scalability. Say in Fernando's example of the department store, you have employees in different departments. You could have just analyzed one department, one very large department or a small department of people. And then we have our graph and we want to scale it to be company-wide, and company-wide could mean enterprise-wide, which could mean a lot of people with a lot of data, and you're trying to synthesize it all down and get the best results. You need to plan for that. You don't want to make a solution that is not going to work as soon as you scale it up. We talked about speed on that other slide, my previous slide, about how fast you'll actually be able to get your matching. You want to know if something works in a second for 100,000 people, what happens when you scale it up? What is happening to that runtime? What is it doing to your technology? And all of this is ultimately going all the way back to that, are we building? Are we buying? What are the metrics? What can we do to make it even better? Third, knowledge transfer protocol development, especially important when we're talking about building and buying. If you're buying your solution, you need to know, what can I influence? What is mine? What is theirs? I'm sorry, I skipped to the ownership bit, but let me go back to knowledge transfer, because that's ultimately very important. The person who's building it is not necessarily going to be the person who's maintaining it, who's maintaining your product. You want to know, when that person leaves, or say you're paying somebody to build it for you, you want to know everything about that system. You want there to be no questions. We want transparency over time. So that's why this knowledge transfer protocol is so important. Now skipping down to this ownership and IP protocol, specifically with the buying situation here. If everything is being managed by a third party, it's ultimately out of your hands, as Fernando was talking about. So you want to make sure that you know exactly when updates can happen, because that is going to ultimately affect all of those downstream processes that we talked about on the previous metric slide. You want to know what's yours. You want to know when you can make changes and what changes you can ultimately make. So all of those constraints, super important to consider when you're thinking about your use case and what kind of solution you want to build. And last but not least, legal considerations. As Fernando said, in what's common to all identity graph solutions, you're going to have some level of compliance to consider, whether it's GDPR compliance. We want to talk about different states in the United States and rules about privacy. Where's your data coming from? All of these things are really important to consider when you're starting from the top in your business and technical specifications. What do I have? What can I use? Do I actually have that? And make sure that your solution is ultimately going to meet your ends and not be breaking any rules. So that brings us to the end of our presentation here on identity graph solutions. We've covered a lot of ground. We've been from how do we build the graph, what sources are we using, the ideas for how we want to process it, determining whether your graph solution is actually good and effective or not, all the way down to what you should consider before you even start, during, and the metrics that you can test for after. So thank you all for listening to our presentation. I see we have a couple of minutes, and Peo, if you want to take it from here.
Thank you very much. The comprehensive approach was really, really interesting for me. But let's go to the technical specifics. If you have the CEO asking, you have to divulge a bit more details. So how about the blocking and pre-selection approach? I believe you noticed this repeating topic, so please share more. This is with regards to the record matching problem. This is a problem which is close to our mind, so everything you're able to share at this forum will be much of interest.
When you say blocking or pre-selection for identity resolution, can you explain what the
This is the reducing the quadratic complexity when you compare two data sets. To avoid comparing everything with everything, you have to separate the data into blocks. Pre-select what are the pairs that you're going to try the matching algorithm.
Definitely. That's we're gonna go into much detail with that, but I can tell you that we can start off with deterministic matching algorithms to get an idea of kind of ground truth individuals that we can identify with known features of them, and we actually take it from there. We start testing algorithms, and we have some sampling strategies, some other forms of analyzing data that is very manual at points, so that we can ensure that we are matching equals to equals and that we're not comparing everything to everything. We filter them down depending on the features that we're selecting. For example, you can filter them down by some distance metric. I cannot go into specifics, but distance metrics are very useful in narrowing down what needs to be compared with what.
Good. Thank you very much. Again, I see Eliza has a question, but Eliza, apologies, we are running out of time. So if you can connect on the platform and discuss this in detail, because you're touching a really interesting topic. And for now, I'll thank you again. And yeah, it's been really a pleasure to listen to your presentation. Eliza, sorry, we are out of time. Please use the platform. Apologies. Well, bye. See you in the next session.
Thank you.
Thank
Thank you, everyone.
you.